There is a kind of fear that comes from seeing a monster. A black hole. A supernova. A gamma-ray burst. A star swallowing a planet. A galaxy colliding with another like a slow-motion pileup of suns. Those fears are easy to understand because they arrive with pictures. They give the mind something to grip. A shape. A disaster. A place to point. The vacuum of space offers no such kindness. It looks like nothing. It behaves, at first glance, like nothing. It invites the oldest and most confident mistake in human thought, that emptiness is absence, that what is not visibly there is not doing anything, that the dark between objects is merely the stage on which reality performs. Modern physics has spent more than a century dismantling that comfort. Because the vacuum is not simply the absence of matter. It is not a passive blank. It is not an inert background waiting patiently for particles, stars, and galaxies to arrive and give it meaning. The vacuum is structured. It is lawful. It is active in ways that are subtle, measurable, and in some cases terrifying. It may determine what particles can exist, how forces behave, how masses emerge, how the universe expands, and whether the very state of reality we depend on is stable. And that means something deeply unsettling. The emptiest thing in the universe may not be empty enough to trust. Scientists do not fear the vacuum because it is boring. They fear it because it may be the quiet condition beneath everything we call normal. The vacuum is not a blank page. It may be the paper reality is written on. And if the paper itself is strange, unstable, contingent, or misunderstood, then every structure drawn upon it, atoms, stars, chemistry, biology, memory, civilization, inherits a hidden vulnerability from the background it never notices. That is the fear. Not that empty space contains a monster. But that empty space may be the deeper medium from which all monsters, all laws, all forms, and perhaps all risks emerge. Tonight, we are going to follow that fear carefully. Not through science fiction. Not through internet mythology. Not through fake claims that physicists have proven reality will collapse tomorrow. We are going to follow it through the real physics of emptiness, from classical ideas of nothingness to the quantum vacuum, from fields and fluctuations to the Casimir effect, from the Higgs field to vacuum energy, from the cosmological constant crisis to the disciplined terror of false vacuum decay. And by the end, the vacuum may no longer feel like nothing at all. It may feel like the most loaded silence in the universe. If you could remove every planet, every star, every atom, every grain of dust, every photon, every molecule, every drifting ion from a region of space, what would be left? For most of human history, the instinctive answer would have been simple. Nothing. A void. A container emptied of contents. A mute interval between things. That intuition is not childish. It is almost unavoidable. Human beings are built to think in objects. We see apples, stones, rivers, bodies, clouds, buildings. We learn to identify what is there, and then we imagine that whatever remains after removal is merely lack. The world, to ordinary perception, appears to be made of things sitting inside emptiness. Physics has made that picture harder and harder to defend. First, relativity taught us that space and time are not passive backdrops, but participants in reality's structure. Geometry bends. Distances are dynamic. Gravity is not just something that happens in space, it is deeply tied to spacetime itself. Then quantum theory made the problem worse. Because in quantum field theory, the vacuum is not a dead void stripped of significance. It is the lowest energy state of fields that fill the universe. And those fields do not go neatly silent just because no particles are present in the classical sense. There are still fluctuations, still constraints, still structure, still laws encoded in what empty space permits and forbids. That alone would be enough to make the vacuum conceptually important. But physics kept going. The Casimir effect suggested that even nothing can produce measurable forces under the right conditions. The Higgs field taught us that empty space itself helps set the behavior of mass-bearing particles. The cosmological constant problem revealed a devastating mismatch between naive vacuum energy estimates and the observed expansion of the universe. And the idea of false vacuum decay raised a possibility so cold that it barely feels like an event at all, that the vacuum state underlying everything we know might not be the deepest one available, and that if it ever changed, reality itself could be rewritten faster than warning. This is why serious physicists sometimes sound uneasy when they talk about emptiness. Not because they are mystics. Not because they are secretly hoping for cosmic horror. But because they know something the human imagination resists. Empty space is not just where things are not. It may be what determines what things can be. That is a much more dangerous role. A vacuum is easy to ignore if it is only absence. It is much harder to ignore if it is arrangement. Harder still if it is active arrangement. And hardest of all if the apparent stability of the world depends on that arrangement remaining exactly what it is. The terrifying reason scientists fear the vacuum of space is not that the universe contains empty regions. It is that empty may be the wrong word for the deepest background state we know. And if the background is loaded, then the rules of reality may be resting on conditions more fragile, more contingent, and more poorly understood than common sense ever imagined. So we begin where all great misunderstandings begin. With a word. Nothing. The word nothing is one of the most dangerous words in human thought. It feels clean. It feels final. It feels obvious. And that is exactly why it misleads us. When we say nothing in ordinary life, we usually mean nothing relevant to us. No furniture in the room. No one at the door. No noise in the hallway. No clouds in the sky. But even these are local conveniences, not deep ontological statements. A seemingly empty room still contains air, thermal radiation, electromagnetic fields, microbes, dust, gravity, chemical traces, and space itself. A quiet hallway still hums with molecular motion. A clear sky still blazes with invisible signals. Human beings rarely encounter true emptiness, if such a thing even exists. We encounter reduced clutter. That matters because our intuition about the vacuum inherits this linguistic shortcut. We imagine empty space as the ultimate version of the same thing, all contents removed, all activity absent, all significance gone. Yet physics keeps discovering that what remains after we remove visible matter is not trivial residue. It is a structured physical state. This should not surprise us as much as it does. Human cognition evolved to track middle-sized objects under survival pressure, not to read the ontology of the universe. Our brains are excellent at noticing fruit, predators, cliffs, social faces, and moving threats. They are not naturally equipped to distinguish between a classical void and the lowest energy state of quantized fields. So the vacuum inherits a false simplicity from language itself. Nothing sounds safer than something. It sounds less expensive, less dangerous, less demanding. If a room is full, you ask what is in it. If it is empty, you stop asking questions. Modern physics says that was a mistake. Because the vacuum is where some of the deepest questions begin. What is the ground state of the fields? What symmetries does empty space preserve? What values do those fields take even in apparent absence? What energy belongs to the vacuum? How does the vacuum gravitate? Can the vacuum change? If it changes, what becomes of the laws built upon it? These are not decorative concerns. They reach into the structure of every atom and every galaxy. And once you take them seriously, the word nothing starts to look less like a description and more like a confession of ignorance. This is one of the recurring themes of our documentary. Empty space may be less absence than arrangement. That arrangement may be silent enough to fool the eye. It may be stable enough to support stars and chemistry for billions of years. But silence is not emptiness. Stability is not simplicity. The fear scientists have toward the vacuum is not superstitious fear. It is the fear one feels toward a foundation that turns out to be more elaborate than the building it supports. A building can be repaired room by room. A foundation is different. If the foundation is stranger than expected, then every ordinary fact above it becomes provisional in a deeper way. The human lie called nothing protected us for a long time because it let us stop thinking once objects were gone. Physics took away that protection. And once it did, the history of emptiness changed. There was a time when the vacuum seemed easier to understand. Classical physics, for all its brilliance, invited a picture of the world in which matter and empty space were conceptually separable. Objects existed. Forces acted. Space provided the arena. Even when the details varied, Newton's absolute space, Maxwell's electromagnetic fields, later debates over ether, the vacuum still seemed, at a broad intuitive level, like a background whose job was to stay out of the way. This was never perfectly simple. Electromagnetism already complicated the picture by filling space with field structure. But classical thinking still allowed the hope that if one removed enough matter and radiation, one approached something close to genuine emptiness. A stage. A container. A vast neutrality. That picture failed for several reasons. First, relativity changed what space and time even were. In Einstein's universe, spacetime is not a passive box. It has geometry. It responds to mass energy. It influences motion. It is not merely where physics happens. It is part of what physics is. A vacuum solution in general relativity is not nothing in the everyday sense. It can still contain curvature, gravitational waves, horizons, expansion, and dynamical structure. A region free of matter is not therefore free of physical content. Second, quantum theory refused to let the lowest energy state be featureless. Once fields become quantized, the old dream of perfect stillness becomes unstable. The vacuum is no longer simply what remains when particles are absent in a classical sense. It becomes the lowest state consistent with the quantum rules of the fields themselves. And those rules do not permit perfect classical quiet. Even before we get to the technical language of zero-point energy and fluctuations, we can feel the conceptual change. Classical emptiness failed because it assumed that the removal of objects would eventually leave a neutral backdrop. Quantum field theory says that what lies underneath the objects is not a neutral backdrop. It is a field-theoretic structure with its own behavior, constraints, and energy properties. The change is profound. In classical thought, emptiness was a leftover. In modern thought, emptiness is a state. That is a much richer, much more dangerous category. A leftover asks nothing of you. A state has properties. A state can be characterized. A state can influence measurements. A state can be metastable. A state can interact with boundaries. A state can help determine what counts as a particle at all. This is why scientists do not casually treat the vacuum as trivial. The vacuum is not a philosophical convenience. It is part of the machinery. And because it is part of the machinery, it can no longer be ignored whenever the machinery behaves strangely. This becomes even clearer when we cross into quantum theory proper, where the vacuum stops resembling the old void almost entirely. The quantum vacuum is one of the least intuitive ideas in all of physics, and one of the most important. To understand it, we must let go of the picture in which particles are the deepest furniture of the universe. In modern quantum field theory, the more fundamental description involves fields extending throughout space. Electrons are associated with an electron field. Photons with the electromagnetic field. Quarks with quark fields. Higgs bosons with the Higgs field. Particles are not little independent billiard balls moving through emptiness in the old classical way. They are excitations, localized, quantized manifestations, of underlying fields. So what, then, is the vacuum? It is not the absence of fields. The fields are still there. The vacuum is the lowest energy state of those fields. No real particles present in the ordinary observable sense. No obvious bustle of matter racing around. And yet not a literal zero of all activity. Because quantum theory does not allow every degree of freedom to be simultaneously pinned to exact stillness. The uncertainty principle forbids certain perfect classical quietudes. A field cannot, in the naive picture, simply sit with precisely zero amplitude and precisely zero conjugate momentum in the fully classical way we might want. There remains irreducible structure in the ground state. This is often described in popular science through virtual particles popping in and out of existence. That phrase is vivid but dangerous. It can create the impression that the vacuum is a tiny fireworks display of miniature objects appearing from nowhere like subatomic ghosts. The underlying mathematics is more subtle. What matters is not the cartoon of little particles flickering like sparks. What matters is that the vacuum state has non-trivial quantum properties, and those properties can have physical consequences. In other words, the vacuum is not simply blank because the fields themselves do not vanish when unexcited. They remain present as the possibility space of the universe. This is why the vacuum can still do things without being full of ordinary matter. Boundary conditions can alter vacuum behavior. Curved spacetime can complicate what different observers call a vacuum. Accelerated observers and inertial observers need not agree on particle content in every setting. The distinction between vacuum and excitation is not always globally simple. That sentence alone should make us uncomfortable. The emptiest thing in physics is not even conceptually identical for all observers in all conditions. Already the old intuition has collapsed. The quantum vacuum is quieter than matter, yes. But quiet is not blank. Quiet is not irrelevant. Quiet is not safe. And now we reach one of the most important transitions in the story. Once you accept that the vacuum is the ground state of fields, the next question becomes unavoidable. If fields are more fundamental than particles, then perhaps what we call empty space is full not of objects, but of the conditions from which objects emerge. That shift is where the fear begins to mature. Imagine trying to understand the ocean by studying only the waves. For a long time, that would seem to work. Waves are visible. They move. They crash. They carry energy. You can catalog them, measure them, predict some of their behavior. But eventually you would realize that a wave is not the fundamental thing. It is an event the deeper thing permits. The deeper thing is the water. Quantum field theory asks us to make a similar correction. Particles are real in the operational sense. We detect them. We scatter them. We build electronics and chemistry and stars out of their behavior. But at a deeper level, what modern theory gives us are fields. Electrons are excitations of an electron field. Photons are excitations of the electromagnetic field. The vacuum is not therefore the absence of all physical substrate. It is what remains when those fields are in their lowest allowed states. And because they are quantum fields, those states are not classically inert. This is where fluctuations enter the conversation. Again, we must be careful. The phrase vacuum fluctuations has been simplified so often that it risks becoming magical. The point is not that the vacuum is a haunted house full of literal tiny apparitions. The point is that the quantum ground state contains irreducible correlations and energy-like features that affect what can happen in measurable situations. The vacuum, in other words, is restless in a highly disciplined way. Not noisy like ordinary matter. Not warm like gas. Not structured like a planet or star. Restless according to law. That is more unsettling, not less. Because it means the vacuum is not a failure to find structure. It is a very specific kind of structure, one subtle enough to be mistaken for emptiness, yet real enough to shape experiments. This leads to one of the documentary's central motifs. The vacuum is not a blank page but the paper reality is written on. The paper has grain. The paper has tension. The paper may hold hidden constraints before any sentence is written upon it. And if the paper changes, the writing changes with it. This is why scientists care so deeply about background states. Background states are not scenery. In physics, backgrounds can decide what counts as a particle, what masses appear, what symmetries are preserved, how fields settle, and how energy contributes to spacetime. Space is not simply where events occur. Space, understood through the vacuum, may itself be an active participant in the permitted forms of event. That is a hard idea to digest because it attacks the most basic common-sense picture we have: things in empty places. Physics keeps replacing that picture with patterns in fields, states in geometry, and excitations relative to underlying structure. The world becomes less like furniture in a room and more like stable behavior in a medium whose properties we only partly understand. And when a medium is only partly understood, fear becomes rational. Not theatrical fear. Not superstition. Structural fear. You fear the thing under the floor more than the thing on the floor if the thing under the floor decides what weight the whole house can bear. The vacuum may be that kind of thing. And if that sounds too abstract, there is an experiment famous for giving empty space teeth. For a long time, the vacuum sounded like philosophy wearing equations. Then came effects that could be measured. One of the most famous is the Casimir effect. Place two very closely spaced conducting plates in a vacuum, under the right conditions, and they experience an attractive force. Popular explanations often say that fewer vacuum modes fit between the plates than outside them, creating a pressure difference. The exact interpretation can be framed in multiple mathematically related ways, and physicists debate what language is most conceptually honest. But the broad lesson remains: the vacuum is not trivial. Change the boundary conditions and you change measurable behavior. This matters enormously. Because it means nothing is responsive. Empty space, under the right circumstances, pushes back. That phrase should land. We are not dealing with a mute absence. We are dealing with a structured ground state whose properties can be altered by geometry and constraint in ways that produce real physical effects. Now, we should be careful not to over-romanticize the Casimir effect. It does not prove every wild vacuum story on the internet. It is not evidence that space is secretly an infinite energy reservoir waiting for science fiction extraction. It is not a permission slip for mystical claims about consciousness manufacturing particles from pure thought. It is a precise physical clue with disciplined interpretation. And the clue says this: the vacuum is physically consequential. That alone is enough to disturb the classical imagination. Because if empty space can participate in measurable forces, then the vacuum is not merely where reality isn't. It is part of how reality is. The Casimir effect functions in this documentary as a kind of philosophical hinge. Before it, a skeptical mind can still try to retreat into the comfort that quantum vacuum talk is mathematical abstraction. After it, that retreat becomes harder. There is an observable edge to the claim. Empty space is not indifferent to its own structure. What is so unsettling is not the size of the force. It is the implication. If even a carefully prepared laboratory vacuum is not trivial, what exactly are we living inside on cosmic scales? What does nothing mean in a universe where boundaries, fields, and quantum states interact? How many of the stable facts we depend on are not brute necessities, but consequences of how the vacuum is arranged? The question becomes more severe when we realize that the vacuum does not merely nudge plates in experiments. It also participates in the very architecture by which elementary particles behave. Because empty space is not just active in a generic quantum sense. In at least one crucial respect, it is endowed with a field value that helps shape the world. That field is the Higgs. The Higgs boson made headlines because it sounded like a particle of ultimate importance. And it is important. But the deeper conceptual shock was never just the boson. It was the field. The Higgs field is not a decorative addition to particle physics. It is part of the background structure of our universe. Its non-zero vacuum expectation value means that what we call empty space is not empty of Higgs structure. Even in the apparent absence of particles, the Higgs field does not simply vanish into nothing. It sits in a particular state, and that state matters profoundly. Interactions with the Higgs field help determine the effective masses of certain elementary particles in the Standard Model. Without the Higgs mechanism, the universe as we know it would not have the same architecture. Chemistry, stable matter, and the entire texture of ordinary physical behavior would be radically different. Pause there. This is one of the most direct reasons scientists fear the vacuum. Because empty space is not just where masses move. Empty space helps determine how masses exist. That is astonishing. It means that what feels like the most solid, obvious facts of material reality are not independent of the vacuum. They are entwined with a field configuration that permeates the cosmos. The vacuum is not merely passive neutrality between particles. It is part of the reason particles have the properties they do. And once you understand that, the emotional geometry of the universe changes. You are no longer standing in empty space surrounded by objects. You are standing inside a field-theoretic condition that quietly governs what objects can become. This is why the Higgs discovery was philosophically bigger than the phrase, God particle, ever captured. The spectacle was misframed. The real revelation was not a mystical object. It was a confirmation that the vacuum has content built into its state. Empty space is organized. That organization supports the world. And because it supports the world, the possibility of different organization becomes terrifying. If the Higgs field were settled differently, masses would be different. If masses were different, atoms might not form as they do. If atoms did not form as they do, chemistry, stars, and life would be unrecognizable or impossible. That does not mean our vacuum is about to flip. It means the background state matters more than common sense permits. The vacuum is beginning to look less like blankness and more like a silent agreement among fields. A successful agreement, so far. A stable one, perhaps. But an agreement nonetheless. And agreements in physics can raise the darkest kind of question. What if the agreement is only local? What if it is not the deepest available state? What if what we call reality is built on a contingent settlement rather than an ultimate one? Before we face that question directly, we have to visit one of the most embarrassing and terrifying numerical disasters in science. Because when physicists tried to estimate the vacuum's energy, the result was not merely off. It was catastrophically, almost absurdly, off. There is a sentence in physics so shocking that it almost sounds invented for dramatic effect. The worst prediction in theoretical physics may come from trying to calculate the energy of empty space. That sentence deserves patience. If the vacuum in quantum field theory is not trivial, then it is natural to ask whether its energy should contribute to gravity. After all, in general relativity, energy and momentum influence spacetime curvature. If empty space contains vacuum energy, then empty space should help determine how the universe expands. And indeed, cosmology appears to tell us that something like a cosmological constant or dark energy-like component is influencing large-scale expansion. So far, so good. The disaster comes when one tries, naively, to estimate vacuum energy using quantum field theory with conventional cutoffs. The theoretical value one obtains is staggeringly larger than the tiny value compatible with cosmological observation. Depending on how the estimate is framed, the mismatch is often described as the worst prediction in physics, off by a grotesque amount, not by a factor of 2 or 10, but by something so enormous that ordinary language starts to fail. Why is this terrifying? Because it suggests that one of two things is true, and perhaps both in part. Either our way of connecting vacuum structure to gravity is deeply incomplete, or reality depends on cancellations, mechanisms, or principles we do not yet understand at all. Neither option is comfortable. The vacuum energy problem is frightening not because anyone expects a calculator error to blow up the universe tomorrow. It is frightening because it exposes a seam between our best theories. Quantum field theory and general relativity each work astonishingly well in their own domains, but when we ask them a simple combined question, what does the vacuum weigh gravitationally? The answers become conceptually devastating. This is where the vacuum becomes more than a technical curiosity. It becomes a site of theoretical humiliation. We do not understand why empty space does not curve the universe far more violently, given the naive expectations of our quantum framework. The universe we observe is not the universe those crude estimates would suggest. So something is missing. And when something is missing at that depth, fear is justified. Not panic. Fear. The kind of fear scientists feel when a background quantity that should be foundational instead becomes mysterious enough to threaten the coherence of the frameworks themselves. The vacuum is not just the emptiest state we know. It is one of the deepest places our current theories fail to reconcile what they are saying. This should make the vacuum feel heavier in the imagination, not lighter. Empty space does not merely sit there. It carries one of the most profound unresolved tensions in modern physics. And because this tension connects directly to cosmic expansion, it brings us to a related and even more famous mystery. Dark energy. The universe is expanding. That discovery already changed everything. Then came the second blow. The expansion is accelerating. Some component of the cosmos, whether a true cosmological constant, vacuum energy in some effective sense, or something more exotic, acts as though empty space itself has a repulsive gravitational role on large scales. We call this dark energy because honesty demands a placeholder when understanding is incomplete. Dark energy is terrifying for two reasons. First, it appears to dominate the large-scale energy budget of the present universe. Second, we do not know what it really is. That alone should be enough to unsettle us. The largest-scale fate of the cosmos seems to be controlled by something we understand only through effects, not essence. But the fear deepens because dark energy looks uncomfortably adjacent to the vacuum energy problem. It tempts the mind toward a simple story. Perhaps dark energy is just the vacuum gravitating. Yet the quantitative mismatch between naive quantum expectations and observed cosmic acceleration is so extreme that the simplicity evaporates. We are left in a difficult place. Observed expansion says empty space matters cosmologically. Quantum field theory says empty space should matter in a wildly different way if interpreted naively. And our current frameworks do not provide a finished, satisfying reconciliation. This is the fear of mismatch. A mismatch is not just ignorance. It is structured ignorance at the point where deep theories touch. Scientists can live with incomplete data. They can live with hard calculations. They can live with observational difficulty. What is harder to live with is the sense that reality is making two successful theoretical languages point at the same region of the map while refusing to tell us why the numbers do not remotely agree. The vacuum, once again, becomes the quiet scene of a major conceptual crime. And because this mismatch sits at the level of the universe's expansion, it is not a laboratory eccentricity. It participates in the story of cosmic history itself. If dark energy remains roughly constant, the future involves increasing isolation between gravitationally unbound structures. Galaxies beyond local groups drift beyond eventual causal relevance. The observable future becomes poorer. The universe may keep expanding into a loneliness written into the large-scale role of its own background state. This is a profound emotional inversion. We once feared the vacuum as emptiness. Now we fear it as influence. Not because it swallows us like a monster. Because it may already be steering the long fate of everything. And all of this still remains, in a strange way, the mild part of the story. Because a vacuum that is mysterious but stable is one thing. A vacuum that might not be the final state is another. That possibility leads to one of the coldest ideas modern physics has produced. False vacuum decay. There are dangers that announce themselves. Asteroids can be tracked. Stars can brighten. Storms can gather. Even black holes reveal themselves by the violence around them. False vacuum decay offers no such mercy. The idea, stated carefully, is this: what we call the vacuum state of our universe may not be the absolutely lowest possible energy state. It may be a metastable state, stable enough to persist for unimaginably long times, perhaps vastly longer than the current age of the universe, and yet not truly final. If so, there could exist a lower energy vacuum into which our present state might in principle transition. This is not science fiction in the sense of being invented for spectacle. It arises from serious thinking about field potentials and stability, especially in connection with the Higgs sector and high-energy extrapolations of known physics. But it must be framed responsibly. This is not established doom. It is a theoretical possibility contingent on parameters, extrapolations, and incomplete knowledge. Current discussions of electroweak vacuum metastability are subtle, model-dependent, and not a warrant for tabloid terror. Still, even disciplined possibility can be frightening. Because if our vacuum were metastable and a transition to a lower energy state were triggered somewhere, the consequences could be total. The laws, particle masses, couplings, and structures built upon the present vacuum could change inside the advancing region. Atoms as we know them might not survive. Chemistry might not survive. Matter in its familiar form might not survive. And the truly terrifying feature is this: there would be no warning in the ordinary sense. The transition boundary would move at or near the speed of light. Nothing from it could arrive before it did. No signal outruns the event that destroys the conditions for receiving signals. By the time you knew, in any meaningful sense, it would already be everything. This is why false vacuum decay exerts such a peculiar grip on the scientific imagination. It is not merely destructive. It is structurally destructive. It does not kill things within the existing rules. It changes the rules under which things exist at all. That is a deeper category of threat. A star can destroy a planet and still leave physics intact. A vacuum transition would not merely ruin objects. It could rewrite the stage on which objects are even possible. Now, again, discipline matters. There is no evidence that such a decay is imminent. None. The age of the universe itself places constraints on how unstable the vacuum could be if metastability is real. Catastrophic headlines often ignore this and treat an exquisitely long-lived metastable state as if it were a live bomb with a ticking second hand. That is not science. That is drama. But the absence of immediacy does not remove the conceptual terror. The terrifying reason scientists fear the vacuum is not that it is about to betray us. It is that betrayal is a meaningful category here at all. If the background state of reality could in principle transition to a deeper one, then our existence is not merely local and mortal in the ordinary ways. It is scaffolded by a global physical settlement that may itself be contingent. That is one of the coldest thoughts in modern theoretical physics. And it becomes even colder when we ask what such a transition would feel like. The answer is almost unbearable in its simplicity. It wouldn't. Human beings take comfort in warning. Even when the warning is terrifying, it gives us a structure in which fear can operate. A countdown. A siren. A brightening sky. Something visible on the horizon. Some interval between awareness and consequence in which the mind can at least say, now it has begun. False vacuum decay, if it occurred, offers no such interval. This is not a poetic exaggeration. It is a consequence of relativity. If a transition bubble expanded at the speed of light, then no signal from its approach could outpace the bubble itself. Information cannot outrun the event. You cannot see it coming in the ordinary causal sense because the seeing would require a faster messenger than the thing you are trying to detect. This is perhaps the most philosophically cruel feature of the idea. Many catastrophes preserve perspective. This one would erase perspective along with structure. There is no heroic last look. No civilization-wide broadcast. No final telescope image of doom crossing the void. Only the fact that, if the vacuum changed, the region inside the new state would not continue according to the familiar arrangement of particles and forces we rely on now. Again, we must remain disciplined. This is a theoretical possibility, not an observed process. But precisely because it is a possibility about the ground state of reality, its emotional force is immense. The vacuum transition is the perfect anti-monster. It has no face. No sound. No shadow. No malice. No hunger. It is not a thing hunting through space. It is a change in the condition of space. That is why it is more unsettling than many cinematic disasters. It is not violent in the way the human nervous system expects violence to behave. It is not an intrusion from outside the normal order. It is the normal order revealing that its deepest background might not be final. We fear visible monsters because they can kill us. Scientists fear the vacuum because it may be the quiet condition beneath everything we trust. And if that condition can change, then safety becomes harder to define. It is not enough to be far from stars, far from black holes, far from radiation, far from impact hazards. None of those distances matter against a catastrophe that is not an object in space, but a transition of space's own fundamental state. This is the part of the documentary where the vacuum stops feeling like an abstraction and begins to feel existentially intimate. Every atom in your body. Every bond. Every stable orbit. Every law-like regularity that let life emerge and thought organize itself. All of it may depend on the vacuum remaining what it is. That sentence alone is enough to explain why serious physicists do not laugh when the vacuum enters the room. Because by now it is clear that the vacuum is not simply one more topic. It is the hidden condition of all topics. At this point, the vacuum may sound like a threat. But that is only half the truth. The vacuum is frightening not only because it may be unstable seeming or poorly understood. It is frightening because it is the quiet condition that makes ordinary physics possible in the first place. That is a subtler, deeper reason. We often think of laws as abstract rules floating above reality, governing events from a kind of mathematical distance. But in practice, laws are realized through structures, field content, symmetries, coupling constants, background states, vacuum expectation values, and the geometry of spacetime itself. The vacuum is not just a leftover state beneath the laws. It is part of how lawful behavior is embodied. This matters enormously. Stable atoms require certain masses and charges. Stable chemistry requires certain electromagnetic and quantum structures. Stars require certain balances of gravity, nuclear physics, and radiative transport. Life requires elaborate layers of regularity, from particle behavior to molecular bonding to thermodynamic gradients. Those regularities do not hover free from the physical state of the universe. They are enacted through it. In this sense, the vacuum is not the absence of order. It is a container of order-bearing conditions. That is why empty space may be less absence than arrangement. We live inside an arrangement so successful that we mistake it for inevitability. This is perhaps the deepest emotional lesson of the vacuum. The more physics learns, the less the world looks like raw necessity and the more it looks like a stable pattern resting on underlying conditions. Some of those conditions may be explained by deeper theory eventually. Some may be contingent in ways we do not yet know. But in either case, ordinary reality stops looking self-sustaining. It starts looking inherited. The fear scientists feel here is almost architectural. If the vacuum helps set the terms of mass, force behavior, and cosmological expansion, then the vacuum is not scenery. It is load-bearing. And load-bearing structures attract a different kind of concern. You stop asking merely what objects do within the universe and start asking what the universe itself is leaning on. This is also why the vacuum can feel philosophically larger than particles. Particles are events or excitations. The vacuum is background state. An individual excitation can vanish without rewriting the world. A change in the background state could. So when scientists study the vacuum, they are not just studying emptiness. They are studying the nearest thing we have to the physical condition of normality itself. That is a terrifying object of study. Because it suggests that what we call normal may be neither simple nor guaranteed. Still, we must not let terror erase discipline. By now we have moved through established physics, interpretive language, and some frontier possibilities. We need a clean sorting. What do we really know? What is strong but still interpretive? What is speculative and must not be oversold? Precision is one of the few antidotes to cosmic melodrama. So let us sort the vacuum carefully. What is established? It is established that modern particle physics is most naturally formulated in terms of fields, not just particles. It is established that the vacuum in quantum field theory is not equivalent to a classical featureless void. It is established that quantum ground states can have measurable consequences. It is established that the Casimir effect is real, though its conceptual interpretation can be framed in related ways. It is established that the Higgs field has a non-zero vacuum expectation value and that this matters profoundly for particle behavior in the Standard Model. It is established that the universe's expansion is accelerating and that some dark energy-like component or cosmological constant behavior is needed in our best cosmological models. What is strongly motivated but not fully resolved? It is strongly motivated that the vacuum energy problem reveals a deep mismatch between naive theoretical expectations and observed cosmology. It is strongly motivated that our present understanding of vacuum structure, gravity, and quantum fields is incomplete. It is strongly motivated that the vacuum is not nothing in the ordinary sense and that background states matter for the properties of reality. What is interpretive or frontier level? The best language for vacuum fluctuations and virtual particles remains interpretive and context dependent. Whether dark energy is literally vacuum energy in a simple sense remains unresolved. Whether the electroweak vacuum is absolutely stable or only metastable depends on extrapolations, precise parameters, and assumptions beyond experimentally settled territory. What is speculative and must be framed cautiously? False vacuum decay as an actual future event is speculative. Claims that the vacuum could collapse at any moment in a practical near-term sense are unsupported. Grand claims that particle accelerators or ordinary astrophysical processes are recklessly endangering the vacuum are not justified by serious physics. Many internet versions of vacuum catastrophe are sensational distortions, not science. This sorting matters because fear without categories becomes myth. But fear with categories can become wisdom. The wisdom here is not that we are doomed by emptiness. It is that the vacuum deserves respect because it is physically deep, conceptually loaded, and still not fully understood. We should neither trivialize it nor turn it into tabloid apocalypse. The disciplined conclusion is stronger than either extreme. Empty space is active enough to matter, foundational enough to structure reality, mysterious enough to expose theory limits, and possibly contingent enough to justify profound unease. That is already more than enough. And once you see it clearly, a striking pattern emerges. Scientists often fear background states more than visible monsters. There is a reason for that. Visible monsters are easy. A black hole is terrifying, but it is local. A supernova is catastrophic, but it is an event. A neutron-star collision is violent, but it obeys the rules while it happens. Background states are different. A background state determines the arena in which all local events occur. If the arena is stable, then even terrible objects remain comprehensible. They can destroy bodies, planets, civilizations, perhaps whole biospheres. But they do so inside a world whose grammar remains intact. Scientists fear background states because background states hold the grammar. This is why the vacuum outranks many more cinematic threats in conceptual seriousness. A visible monster kills within the rules. A background instability threatens the rules beneath the killing. It does not merely end structures. It raises questions about how structures are licensed in the first place. This difference runs through the whole history of physics. The deepest revolutions do not usually come from discovering one more object. They come from revising the background. Space is not absolute, time is not universal, matter is not fundamental in the old sense, emptiness is not empty, gravity is geometry, the vacuum is structured. Each step makes the world less like a set of things in a box and more like behavior emerging from underlying conditions. That is not a comforting trend. Because conditions can be harder to picture and harder to guarantee than things. A monster has edges. A background state does not. You can hide from a storm. You can avoid a star. You can move away from a black hole if you are far enough and wise enough. What do you do with the fact that the emptiness between all objects may be the most physically consequential thing of all? What do you do with the possibility that the world's apparent stability depends on a silent state you barely understand? You do what physicists do. You measure what can be measured. You separate strong theory from wild speculation. You search for deeper frameworks. And you allow yourself a disciplined form of fear. This kind of fear is not weakness. It is realism. It is what happens when the foundations stop looking self-evident. The vacuum has that effect because it changes the emotional hierarchy of the universe. The deepest danger is no longer necessarily what explodes or consumes. It may be what quietly supports everything until one asks what that support actually consists of. The terrifying reason scientists fear the vacuum of space is not that emptiness hides monsters. It is that emptiness may itself be the most important physical condition we do not yet understand. And once that idea enters the mind, it changes even our psychology. Because it means nothingness is no longer empty enough to soothe us. There are scientific discoveries that wound the ego. Earth is not the center. The sun is one star among many. The galaxy is one among billions. The universe is older and larger than myth permitted. Human intuitions about space and time are provincial. Then there are scientific discoveries that wound something deeper than ego. They wound our category of safety. The vacuum does that. Why? Because the mind relies on emptiness as a psychological refuge. When the room is crowded, one looks to the gaps. When the world is dangerous, one imagines open space. When objects become threatening, one trusts the background. Empty space, in human imagination, is where danger is not. Modern physics destroys that refuge. It tells us that the background is structured. That the silence carries law. That the apparent blankness may be active, load-bearing, and not fully secured in the way intuition wants. This is a psychological shock of a rare kind because it attacks one of the oldest informal metaphysics we have, that nothing is the simplest thing there is. The vacuum says no. Nothing, or what we loosely call nothing, may be one of the most complicated states we ever encounter. That reversal is hard for the mind to metabolize. It means absence is no longer absence. It means the dark between stars is not merely a visual gap. It means emptiness is not where explanation ends, but where some of the deepest explanation begins. There is also something almost spiritual in the discomfort, though the physics itself is not spiritual. Human beings want the world to rest on something intuitively clean. A base layer. A bottom floor. A final simplicity. The quantum vacuum denies that wish. The deeper we go, the less reality resembles plain stillness. Instead, it resembles structured potential, silent constraint, and hidden dependence. The universe begins to look less like a collection of solid things and more like a stable negotiation among fields, symmetries, and states. That is beautiful. It is also destabilizing. Because negotiations can fail. States can be contingent. Symmetries can break. Backgrounds can matter more than the objects they host. Which leads to one of the hardest emotional questions in the whole story. If empty space is contingent, what does safety even mean? We are used to defining safety geographically. Far from the cliff. Far from the radiation source. Far from the fire. Far from the war. Far from the black hole. But what if the relevant danger is not local in that way? What if the stability of your world depends not only on where you are, but on what background state reality itself occupies? Then safety changes meaning. It is no longer merely distance from visible hazards. It becomes dependence on invisible regularities. This is already true in ordinary life, though we seldom notice. You are safe not only because no predator stands nearby, but because electromagnetism behaves reliably, chemistry remains stable, the Earth's gravitational environment is moderate, and the nuclear processes in the Sun remain within the range that lets a biosphere persist. Most safety is inherited from background regularity long before it is defended by personal action. The vacuum takes that lesson to its absolute limit. If the vacuum helps determine the mass behavior of particles, the expansion history of the universe, the form of the ground state, and the permissibility of stable structures, then safety is built on a condition deeper than any ordinary shelter. Safety becomes metaphysical in the most physical sense. It becomes trust in the background. That is a hard thing to live with once seen clearly. Because the background is not something we built. Not something we negotiated. Not something we can inspect in full. Not something we fully understand. We live inside it. We inherit it. We study it after the fact. And the more we study it, the more it looks like a successful arrangement rather than a trivial necessity. Now, one could respond with despair. But that would be a mistake. Contingency is not the same as imminent failure. Fragility is not the same as present collapse. Mystery is not the same as catastrophe. The disciplined lesson is not that we should panic about the vacuum. It is that reality's quietest layer deserves more awe, more caution, and more humility than human intuition naturally grants it. The vacuum is frightening precisely because it does its job so well. It lets us forget it is there. It makes ordinary matter possible. It supports stable law long enough for stars, chemistry, and life to arise. It is quiet enough to be mistaken for nothing and deep enough to carry the burden of everything. That combination is what makes it terrifying. A visible danger at least announces itself. The vacuum may never do that. Its greatest power lies in how completely it can be ignored by the creatures whose entire existence depends on it. And that returns us to the core motif we have carried from the beginning. Empty space may be less absence than arrangement. If that is true, then the vacuum is not the end of explanation. It is the place where explanation becomes most unnerving. All that remains is to gather what we have learned and say the final thing plainly. Let us say it carefully. Scientists do not fear the vacuum of space because space is empty. They fear it because empty space is not empty enough. The old human picture imagined the vacuum as a blank backdrop, a passive darkness between meaningful things. Modern physics has taken that picture apart piece by piece. Fields remain where particles are absent. Ground states retain structure. Quantum fluctuations and boundary-sensitive effects reveal that nothing has physical consequence. The Higgs field shows that empty space helps determine the behavior of matter. Dark energy suggests that the background state of the cosmos participates in its large-scale fate. The cosmological constant problem exposes a wound between deep theories. False vacuum decay, while speculative, reminds us that the apparent stability of the world may rest on a state whose finality is not guaranteed by intuition alone. Taken together, these facts and possibilities create a new emotional map of the universe. The vacuum is not a blank page. It is the paper reality is written on. And that paper may be active, law-bearing, tension-filled, and not yet fully understood. This is the quiet terror beneath reality. Not a beast hiding in the dark. Not a secret object drifting between stars. Not even, at the deepest level, one more dramatic catastrophe. The terror is structural. It is the realization that what we casually call empty space may be the condition beneath everything we trust: mass, force, stability, expansion, causality-friendly order, and that our understanding of that condition remains incomplete at exactly the points where our greatest theories should meet. That does not mean the universe is unsafe in any childish sense. It does not mean tomorrow will bring vacuum collapse. It does not mean cosmologists are secretly waiting for reality to blink out. What it means is colder and more profound. The world may depend on background conditions more contingent, more subtle, and more physically rich than ordinary intuition ever allowed. We do not merely live among objects. We live inside an arrangement. That arrangement has been kind enough, so far, to permit stars and biospheres and mathematics and memory. Kind enough to let hydrogen become galaxies and galaxies become carbon and carbon become questioning minds. But kindness is the wrong word, because the vacuum is not benevolent. It is simply successful. And success can be mistaken for inevitability. Physics warns us against that mistake. It tells us that the most stable-looking facts may be inherited from deep conditions. It tells us that silence may conceal structure. It tells us that emptiness may be one of the least empty things in the universe. It tells us that what feels like the safest part of reality may, in truth, be the least understood layer beneath every other layer. That is why scientists fear the vacuum. Not because it is a void. Because it may be the deepest physical medium we misunderstand. And where we misunderstand the background, every ordinary certainty becomes a little less absolute. The stars still shine. Atoms still hold. Galaxies still turn. The equations still work astonishingly well. But underneath all of that is a fact the modern universe keeps forcing upon us. Reality is not built on obvious emptiness. It is built on a silent state whose apparent simplicity was one of the greatest illusions human beings ever believed. So if there is a final line to carry out of this documentary, let it be this. The terrifying reason scientists fear the vacuum of space is not that the universe is empty. It is that the universe may depend on a background state far stranger, more active, and perhaps more contingent than human intuition ever suspected. And if empty space is not the absence of reality, but the loaded condition that makes reality possible, then the darkest regions of the cosmos are not where physics disappears. They may be where physics is deepest.